Welcome back. In this lecture, we'll introduce the engineering energy equation and its application. Energy equations can be extended to include cases the mechanical work is done by the fluid, as in the case of a turbine or a windmill, or it is done on the fluid, as in a pump or a fan. Consider a device with one inlet and one outlet. Introduce a stirrer in this device. Is a device, when rotated, will do work on the fluid. Let the flow through this control volume be steady, incompressible and inviscid. Further, let there be no thermal action, that is, there is no input or output of energy as heat and therefore no change in temperature. Let's also assume that the flow at the inlet and outlet is one-dimensional. That is, we have uniform velocity at 1 and 2. Since there are no shear stresses, the only work done by the surface forces at the control surface is by the pressure forces at the inlet and outlet. And as we showed in the last lecture, the rate of this work done by the system is minus P1 A1 V plus P2 A2 V2. P1 A1 V is the work done on the system while pushing the fluid in at the inlet, and therefore it is negative. P2 A2 V2 is work done by the system in pushing the material out at the exit, and that's why it is positive. Let's assume that the external device on which the system is doing work, or which is doing work on the system, at a rate of W dot S. The subscript S stands for shaft, because this usually is a work through a rotating shaft. Thus, W dot S is the rate of doing work by the system. In this case of the stirrer, Ws dot would be negative. So the total work done by the system then is minus P1 A1 V1 plus P2 A2 V2 plus Ws dot. The energy equation for the control volume that we obtained earlier was dE by dt, the material rate of change of the energy contained in the system, is equal to del E by del T, the rate of accumulation of energy within the control volume, plus the net efflux, and this should be by first law of thermodynamics, Q dot minus W dot. The capital E, the total energy contained within the system, can be found out from using the specific energy E, that is the energy per unit mass, which consists of V square by 2 plus Gz plus U, the internal energy. The steady flow requirement states that del E by del T is equal to 0, no accumulation. There is no thermal action, so Q dot is 0, and also U at inlet is equal to U at outlet, since there is no change in temperature. So net efflux of E must equal to Q dot minus W dot. Net efflux of E is m dot, the rate of mass throughput, into V square by 2 plus Gz, the specific energy per unit mass at the outlet, minus m dot, the rate of mass throughput, into V square by 2 plus Gz at the inlet. This is the net efflux of energy, and that should be equal to minus the net work done by the system, and that we have shown is minus P1 A1 V1 plus P2 A2 V2 plus Ws dot. Now rho 1 A1 V1 is equal to rho 2 A2 V2 for a steady system, and that is equal to the rate of mass throughput. And so that A1 V1 is m dot divided by rho 1 and A2 V2 is m dot divided by rho 2. Using this, we can divide the energy equation by m dot throughout, and we get the relation by rearranging v square by 2 plus gz plus p by rho at the outlet minus the same quantity at the inlet is equal to minus ws dot divided by m dot, which is minus lowercase ws dot. Lowercase ws dot is the rate of doing work, shaft work by the system per unit mass of fluid throughput. The same equation rewritten. Now each of the term here has a unit of joules per kilogram. We can divide each terms by G to get an alternate form, V square by 2G plus Z plus P by rho G at the exit. These are the sum of the various heads at the exit. V square by 2G is the kinetic energy head, Z is the potential head, and P by rho G is what is termed as the pressure head. At the exit is equal to the same heads at the inlet minus HS, the work done by the system expressed as per unit weight throughput. Each term has a unit of length in this case. These equations are further extended by considering that the work done by viscous forces as loss of mechanical energy. If there is any work done by viscous forces within the control volume, we'll consider that as a loss of mechanical energy. We use WL dot for the energy lost to the viscous forces per unit mass throughput and HL for the head loss for mechanical energy to viscous forces per unit weight throughput. Thus, we can express the final result. The total head at the outlet is equal to total head at the inlet minus HS, the head of work done by the shaft, minus HL, the head loss due to viscous stresses. This is known as the extended Bernoulli equation or engineering energy equation, any of the two names. A general class of fluid mechanical problem, for example, those involving fluid machineries like pumps, turbines, etc., consists of cases where the fluid field is not exactly steady but is changing cyclically because of a rotating shaft. Thus, the equation above should hold with the understanding that all quantities are now averaged over a rotational cycle. We introduce now the concept of hydraulic and energy grade lines. Consider a converging diverging channel with a liquid flowing in this. Simple application of Bernoulli equation would show that as the fluid moves down this converging diverging channel, in the converging portion the velocities would be increasing and so the pressure would be decreasing. In the diverging portion the velocities would be decreasing and the pressure would be increasing. Thus, the piezometric tubes that are attached to the channel would show a level of water first decreasing and then increasing as shown. This represents the variation of piezometric head along the length of the channel. It represents Z plus P by rho G. This is called the hydraulic grade line in civil engineering. There is another concept, the energy grade line, which is shown horizontal, constant across this section, because there are no losses and there is no shaft work done. So the Bernoulli equation would require that the total energy, the kinetic plus potential plus the pressure, would be constant. So the variations in this case are only in the hydraulic grade line. The energy grade line is constant. An interesting property of this grade line is that both the hydraulic grade line and the engineering grade line do not depend upon the inclination of the channel. If this channel were inclined at an angle as shown, as you go up the channel, the elevation head would increase, but the pressure head would decrease accordingly, so that the hydraulic grade line would have exactly the same shape as before, and as would the energy grade line. Let's do an example of plotting the hydraulic grade line and energy grade line in flow over a weir. In an open channel, we have an obstruction we call a weir, and the flow is taking place above the weir, like we did in the last lecture. This is one approximation to the flow that we can take. I draw a line at 45 degrees. At any height y above the crest of the weir, the arrow here shows the elevation head. Since this line is 45 degrees, this horizontal line marked elevation head is exactly equal to the height of this point above the base. So the pressure head all across this jet of water that emerges over the weir is atmospheric all through. And so the pressure head is assumed 0. We talk about the gauge pressure. The hydraulic grade line then looks like this, because pressure head is 0. So the elevation head line and the hydraulic grade line would be same. The hydraulic head is maximum here and is minimum here. Now, since the water is coming from a reservoir which is essentially at rest, the total energy along any streamline is the same. So, at every point along this line, the total energy is the same. And so, the energy grade line would be a straight line. At the top, the velocity is 0, and so the total energy is the hydraulic head plus the velocity head. So, same point, and this is the energy grade line. Clearly, the shaded area represents the velocity head. The velocity head is 0 at the top and is maximum at the bottom, varying linearly. I have plotted here the hydraulic and the energy grade line in a converging diverging channel. In the first picture on the left, we have a channel in which there is a short converging portion and a very long diverging portion. The total energy shown by a blue line is constant. As the flow travels downstream, the velocity increases, and so the pressure decreases. And then, after the throat, since the area is increasing, the velocity decreases and the pressure increases. The red line shows the hydraulic grade line, pressure plus the elevation. The elevation is constant, so the pressure line itself is the hydraulic grade line. The shaded portion represents the velocity head, the difference between the energy grade line and the hydraulic grade line. This picture changes drastically if the diverging portion of the channel is short. As we have discussed a couple of times earlier, now that the boundary layer forms along the channel separates at the throat in the diverging portion, and the liquid comes out as a jet. And since the liquid comes out as a jet, its velocity does not decrease, and so the pressure does not increase. As the red line here shows, the pressure does not recover back to its original value at the inlet. There is a loss of pressure. The jet ultimately fills the channel, and the kinetic energy of this jet is then dissipated and is lost. The same principle is used in the design of wind tunnels. A wind tunnel is a structure to test aerodynamic phenomena, aircraft parts, or similar things in a fluid flow. When the aircraft moves in a stationary atmosphere, the forces that is experienced are the same. When the aircraft is stationary and the air moves past this, so we use this principle to construct a wind tunnel. In this test section of the wind tunnel, we mount a model of the aircraft part that we want to test, and we create a flow in this channel. This flow is created by a fan in this portion which sucks air. The inlet of this tunnel is designed such that the flow that we obtain in the test section is uniform and straight. This flow needs to slow down at the fan. And so the diverging length, termed the diffuser, is much longer than the converging length. This is to prevent the separation of the flow in the diverging portion. These wind tunnels can be small or can be big. One of a very big tunnel exists in IIT Kanpur, where in the National Wind Tunnel Facility, we have a closed circuit wind tunnel. The fan sucks in air and flows, the air slows down, it bends along, it goes again. The screens in this inlet section are there to make the flow smooth. The air is speeded up in this nozzle, and this is the test section where the parts that we want to study the flow on are mounted with proper instrumentation. The flow then slows down in the increasing section and is recirculated. The recirculation is there essentially to save energy. Let's apply the engineering Bernoulli equation to a pump. In this example, a pump is used to pump water through a height. The pump picks up water from this tank to this pipe, and the water is now pushed through a pipe at a section A2 at a height. Let's take a control volume shown by these broken lines. Assuming incompressible and steady flow with negligible heat transfer, we can apply the engineering Bernoulli equation to the control volume shown. The steadiness of the flow through rotating machinery here is in the context of the quantities averaged over one rotation of the impeller as discussed earlier. So, the applicable equation is the engineering Bernoulli equation or the extended energy equation. Here, we know at 1 the inlet, the surface of the tank from where the water is coming from. If the cross-sectional area A1 is very large compared to the area A2, then the velocity at 1 is negligible. Z1 is taken to be 0. We define the datum there. Z2 is given. We know the height to which we are pumping water. P1 and P2 are both P atmospheric. Let's neglect the losses. So, WL dot is taken as 0. Now, we are given m dot, the mass flow rate through the pump, and know the diameter of the system. We can determine V2, the velocity through the pipe. Let's assume the whole pipe has the same diameter. So, the velocity throughout the pipe is V2, the velocity at the exit. We are to find the power consumed by the pump in pumping m dot kilogram per second of water to the height h. Ws is what we want to calculate, and then we can find out capital Ws dot is equal to m dot lowercase ws dot. Recall that lowercase ws dot is the work done per unit mass throughput, while capital Ws dot is the total work done per unit time by the system. Let's plot the hydraulic and the energy grade line. Let Z is equal to 0 represents the datum. Then the total head. Total head up to the inlet is constant and is 0, because at 1 the pressure is 0, Z elevation is 0, the velocity is 0. So that the total head is 0. And since along any streamline from here to any point within this pipe, we can apply Bernoulli equation. So the total head remains the same at 0. The pump increases the head. Pump does work on the system. So HS is negative, and that increases the head of the fluid, as the total head is now in the exit pipe is at an elevated level. This is HS, the head supplied by the pump. It is actually a negative quantity because this is the work done on the system. Since the pipe has a constant diameter, the velocity is constant throughout the pipe, and so the velocity head is a horizontal line. Clearly, the piezometric head, which is the sum of the elevation head and the pressure head, is equal to the total head minus the velocity head. So piezometric head is a line which is below the total head line by an amount equal to the velocity head there. And this line then represents the piezometric head. We have negative piezometric head through the inlet pipe and the positive piezometric head at the outlet pipe. The pressure head and the elevation head together makes the piezometric head. So pressure head we can obtain by subtracting the elevation from the piezometric head. This elevation we subtract from the piezometric head to get this broken line. This is the pressure head. Let's take another example. It concerns a hydroelectric project where the water is stored up behind a dam. That water is directed through a tube or a pipe or a channel known as penstock to a turbine. It extracts energy from the water, and the resulting flow passes through the end of the penstock into atmosphere. Let's draw the total energy line and the hydraulic line for this. Let us consider this as a relevant control volume with one inlet at 1, where the velocity can be assumed to be 0, the pressure is 0, the elevation head is h, and at 2, where there is a velocity, the pressure is 0, the atmospheric, and the elevation is 0 since we take the datum there. Let Hs be the head extracted by the turbine and converted to work. So neglecting viscous losses in the pipe, the engineering Bernoulli equation requires V square by 2G plus Z plus P by rho G at the outlet 2 is equal to the total head at the inlet minus Hs, the head extracted by the turbine. This is the work done by the system, so Hs is positive. Let the velocity at point 2 be V. So the first term V square by 2G at the exit is V square by 2G. Z is 0, pressure is 0, that equals velocity 0 at point 1, the elevation capital H at point 1, the pressure is 0 at point 1 minus Hs, the head extracted. So we get head extracted is equal to capital H minus V square by 2G. This we could have seen directly. From the total head H available in the reservoir, we extract all of it in the turbine except for the head of kinetic energy that the water emerges with at point 2. Thus, Hs is equal to capital H minus V square by 2G is the energy extracted per unit weight of the fluid passing through. The weight passing through per second is rho VA times G. VA is the volume passing through, rho VA gives you the mass passing through per unit time, and multiply by G will give you the weight of water passing through per unit time. So the power output is rho VAG times HS, which is rho AG capital HV into 1 minus V square by twice GH. Now this is an interesting expression. Here, as V increases, this increases, but this decreases. So one part increases, the other part decreases. When V is equal to 0, clearly the power would be 0. When V is equal to under root 2 GH, that is all the head from the reservoir is now available as a kinetic head, that is no head is being extracted, then this term becomes 0. So there must be a maxima somewhere in between. Here the term 1 minus V square by twice GH represents the fraction of the total available head which is extracted by the turbine. We plot here the non-dimensional velocity V by under root twice GH against the non-dimensional power developed by the system. And we notice that there is a maximum power available. We non-dimensionalize the power output Ws dot with rho A GH raised to power 3 by 2. This is the total power that would be available if we extract all of this out from the system. And we non-dimensional velocity by under root twice GH, which would be the velocity if the total head is converted into velocity. And so we get a non-dimensional power Ws dot star equal to under root 2 V star into 1 minus V star square, where V star is V by under root twice GH. So the velocity for the maximum power we can determine is V star is equal to under root 1 by root 3, and the maximum power output non-dimensional is Ws star is equal to 0.543. We plot the energy grade line and the hydraulic grid line for this hydropower setup, and we do this in inclined coordinate system. Let Z0 line represents the datum, the elevation head, the pressure head. As we go down, the pressure increases. In the turbine, the pressure becomes negative after a while, and then it increases in the tail race. The hydraulic grade line is then the sum of the pressure head and the elevation head. The hydraulic grade line here is a constant value. The velocity head is constant through the pipe if we assume the diameter of the penstock and the tail race is constant. The total head is the energy, the hydraulic grade line plus the velocity head. through the pipe. Head extracted by the turbine is shown here. Let's do another example of flow in a ducted fan operating in a duct with a smooth bell-shaped entrance. This fan sucks in air from all around and the air exits as a jet. Given the cross-sectional area and given the fan power, calculate the air flow rate. That's the problem. So we assume this control volume. We assume a very large area at the inlet. The air is coming from all sides. The pressure is atmospheric there and the velocity is very small because the area is very large. If the air velocity within the duct is not very large, the flow can be considered as incompressible. Averaged over one rotation of the fan, the flow can be taken steady. We neglect the viscous losses. The flow meets all the requirements of the engineering Bernoulli equation. And so we apply this equation. V square by 2G at the exit, Z at the exit is 0, P at the exit is 0 is equal to V square by 2G at the inlet is 0, the elevation Z is 0, pressure at the inlet is 0 again minus Hs. So this gives you V square is equal to minus twice GHs. Since the fan does work on air, Hs is negative. Hs is the head supplied by the fan. Let's plot the variations of the heads. The total head up to fan is 0 because the total head here is 0. Up till here, up till the fan, there is no input of energy, and if we neglect viscous losses, the total head would remain 0 there. The fan supplies a head, Hs, and so in the remaining part of the tube behind the fan, the total head is this. The pressure head Z is same, so pressure head is same as the piezometric head. So pressure head line is the same as the hydraulic grade line, and it is obtained by subtracting the velocity head from the total head. The velocity starts out at 0 here, it increases and then becomes constant in this duct. So the pressure head looks like this shown here. From the total head line, we subtract the velocity head. In this portion, the velocity is increasing up to the inlet, and after that, the velocity is constant. Ideal velocity head. If there was viscosity present, there would be losses against the walls of the duct, and the total head would decrease constantly. This broken line shows the decrease in total head. The pressure would also decrease constantly along this, and so the real pressure head would be this broken red line, and the real velocity head is this. Let's do one more concept called the kinetic energy correction factor. We have so far assumed that the flow through the inlet and outlet are one-dimensional. That is, we assumed that there are no variations in the velocity across the inlet and the outlet sections. But there actually are. This can be taken care of by using a kinetic energy correction factor. So, we calculate the kinetic energy flux by using the average velocity, and then we multiply it by a correction factor to find out the actual kinetic energy flux. If we have a circular pipe of radius r, then the one-dimensional assumption would require that we assume the velocity is average velocity all across the pipe section. So, V average, VAV, is the velocity throughout the pipe. The mass flow rate would be rho V average times pi r square, and then kinetic energy per unit mass at average velocity is taken as V average square divided by 2. So, this is the kinetic energy flux with one-dimensional assumption. Now, let us assume a laminar flow. In a laminar flow, the velocity profile is given as V is equal to V max into 1 minus r star square, where r star is r by capital R, the radius of the inlet pipe. We have shown earlier that V max is twice the V average. Now, the actual kinetic energy flux would be obtained by considering a ring of thickness dr at radius r. The kinetic energy through this is mass flow through this, which is twice pi r V dr times the kinetic energy of this, which is 1/2 V square per unit mass. And so, this is simplified to pi, rho times pi times integral 0 to r V cube r dr. So, we define gamma, the kinetic energy correction factor, as the actual kinetic energy flux shown in the numerator divided by the kinetic energy flux with one-dimensional assumption, which is obtained in the last slide. And this simplifies to twice integral 0 to 1 V by V average whole cubed r star dr star, where r star is r divided by capital R, the radius of the pipe. Now, we can go the laminar or the turbulent route. For the laminar flow, V is equal to V max 1 minus r star square. V average is 1/2 V max, and V divided by V average is twice into 1 minus r star square. The above integration yields gamma, the kinetic energy correction factor, as 2. We could use turbulent flow also, and in turbulent flow, most commonly used velocity profile is the 1/7 power law profile. V is equal to V max into 1 minus r star raised to power 1/7. V average turns out to be 0.817 V max, and V divided by V average is given by 0.817 into 1 minus r star raised to power 1/7. This yields gamma is equal to 1.058. The kinetic energy correction factor for turbulent flow is very small compared to 1. So, we might as well not use the kinetic energy fraction in the case of turbulent flow. As was mentioned earlier, most pipe flows of commercial interest are turbulent, and so they probably is no need of using kinetic energy correction factors. Thank you.